Okay, so for the last day, we actually discussed mainly about the vernier caliper, and then we started to discuss about the micrometer, screw gauge, and the screw principle. So there we discussed that micrometer screw gauge is a device that is using the screw principle as the measuring principle. So there I discussed about a special rule that we call as the screw principle or the right hand rule. So we can use this right hand rule to identify the direction of the linear motion when an object, when a screw is rotated in some direction. So let me remind you again because this is important. So if you take your right hand and if you keep the right hand fingers curved like this and your thumb perpendicular to those fingers, then if your fingers represent the direction of rotation, then the finger will represent the direction of the linear motion of that one. So there we discussed that. So when a rotational motion is given in the, if I see it from here, if I look from this side, if it is rotated to the clockwise direction, it is moving forward. And if I rotating in the anti-clockwise direction, then it is coming out. So like that way we discussed about that. Right. Okay, then actually we need to discuss about how to find the least count and what is the working principle and how to read the micrometer screw gauge. Right. So let's start from that point today. So let me show you a virtual simulation of the micrometer screw gauge first. Then we will discuss what are the important points to be known. So we actually discuss what are the main components there, and then we'll move into the reading part. So in here you have a virtual micrometer, right? So I will put the background to white, then it's clearly visible to you. Right, okay. So you can see here, this is the structure of the micrometer. So there are few things that should be considered when you are taking a micrometer screw gauge in your hand. So the first one is, as in the vernier caliper, we need to know about what is the minimum measurement that can be taken from this one and what is the maximum measurement that can be taken from this one. That is actually called the range of measuring range. What is the minimum? What is the maximum reading that we can take? Right. Usually a micrometer is used to measure distances very much smaller than 5 centimeters. So actually vernier caliper you can use up to 15 centimeters as I showed you the last day. But in here, the micrometer we do not use for such larger measurements. We use only for very smaller measurements like 3 centimeters or 2 centimeters like that for smaller measurements only. Now, if I completely move the ratchet with the thimble to the other side and check what will be the maximum reading that can be taken from this one. So if I can rotate this one and check. So you see here you can check the screw principle by using this one. So you can take the right hand. Now I will rotate this one. Then you can check to what direction that it will rotate. So I am rotating in the this direction. So you can put your fingers like this way towards your side, and then you can see it is moving to the left side. So the thumb is showing the right hand direction. So that means our screw principle is working for this one. Right. Now, if I rotate to the other side, you can clearly see, the rotating in this direction towards the screen. It is rotating towards the screen, therefore it is moving to the left hand direction. So you can put the screw principle and you can check whether it is working according to the screw principle. Right. So if I completely move this one to the left hand side, then I can get the maximum reading there. So you can see here, this is 0.5 millimeters actually, not 0.5, this is 5 millimeter mark. And I'll try to move it fast here. So it is actually around 2 to maximum 3 centimeters like distance is there, right? So the range of this one will be around 30 centimeters, sorry, 30 millimeters, right? Now let's see the main scale. You can see here the main scale clearly, right? So here you have millimeter marks. Here 0, here 1. Let me take the lesser pointer, then it will be easy for you to see. So these are millimeter scales, 0, 1, 2, 3, 4, 5, like that way. And you have some lines underneath that term. So what are these lines? If you see carefully, you can see this line is in between 0 and 1. Therefore, it is right in the middle of 0 and 1. Therefore, this one is representing 0.5 millimeter mark. 0, 0.5, 1, 1.5, 2, 2.5, like that way. This is how the micrometer screw gauge main scale or the sleeve is marked. Right. Now, if you consider the circular scale, you can see how many components are there. So if you start from here, that is 0 and 1, 2, 3, 4, like that way, it is going in this direction, and it is coming in this direction as 45, 46, 47, and up to here it is 50. So in the circular scale, we have 50 divisions, and in the main scale is divided into 0.5 divisions, right? So if I quickly take that now note, main scale, one main scale division is actually how much length? 0.5 millimeters, right? Because you have to consider the both up and down, because you can clearly mark this one, right? You can clearly mark this 0.5 millimeter. Therefore, the main scale division, the length of one main scale division is 0.5 millimeters. And if you consider the number of divisions, in circular scale, you can see there are 50 divisions in the circular scale. We have checked that one. We have 50 divisions in the circular scale. Now, let's see, these are the information that we have. Let's see how to calculate the least count of this equipment. So the least count is the lowest or the smallest measurement that can be taken from this one, right? So before going to that one, we actually need a special term. Screws has something called a pitch. Screws has something called a pitch. So what do you mean by pitch is, so the distance traveled by the screw linearly. The distance traveled by the screw linearly. So this is the total screw, right? The distance traveled by the screw linearly when one complete rotation is done in the circular part. That is called the pitch. So it's a small word actually, small definition. So we call it pitch. Pitch equals linear distance traveled, linear distance traveled when one during traveled during one complete rotation. This is called the pitch. So pitch is actually for almost all the screws that we find in our day-to-day life. Any screw, usual normal screws also, they have a pitch. So this pitch is actually a characteristic property of a screw. So if if I'm doing an engineering design, let's say if I'm doing an engineering design to design a machinery, then if I need to fix something to something, so actually we call them fasteners. These nuts and bolts are called fasteners because they are used to actually fix two things together. So if you find anywhere there's a screw, there's a fixing, right? Your doors are fixed with the screws, your windows are fixed with the screws, even your laptop is fixed to the frame by using the screws. So when you are designing, you need actually specific screws. So how do you purchase? How do you buy the screw? Is by its pitch and its diameter. So that's how we actually engineers select and buy the screws. Right, so designing screws is a very special thing, and it is manufacturing is a very fascinating process. We call it lathing. There's a machine called lathe machine or a CNC machine. We can use this to fabricate the screws. So they are what we actually, the characteristic property of that screw during manufacturing is also this important property called pitch, right? So that is actually the linear distance traveled during one complete rotation. And the thing is that it is exactly equal to distance between two consecutive screws or threads. We call it threads. Distance between two consecutive threads. Should be TWO, two consecutive threads. Right. Okay. So if I quickly take you to a screw, then we can see actually. So you can see the images. Okay. So this is a very good example. So you can learn about this one. Right. So in this diagram, you see these are called as the threads. You can see they are marked as threads. Right. So you can see there's something called marked as pitch. So this pitch is actually the distance between two threads. It is actually fixed for throughout the entire screw. This pitch is a fixed one. So other you have head and other things are there, but the most important thing is this pitch. And for the engineers, when we are designing, actually we actually care about the pitch angle also. We call this angle. You can see thread angle. We call the pitch angle. That is also considered, but for our case, we only need to know about this pitch. So it is basically the distance between two consecutive threads, and it is exactly equal to the distance traveled when we rotate by one rotation. Right. So if I go here, now if I rotate this one revolution, you check how much distance will it travel, right? So I will first take this one to somewhere clear position, right? I will take it here. Somewhere here I will take it, okay. Okay, now you see zero mark of the circular scale exactly coinciding with the main axis of the main scale. So this middle line is called the main axis of the main scale. Now you can see here the zero of the circular scale. Now let's turn this one, right? Now let's turn this one like this way. So see what is the linear distance traveled by that one. So if you carefully observe, now I have turned 10, 15 turns. So if you turn one revolution means 50 divisions should rotate. 25, 30, 35, 40, 45, and 50. Now exactly I have rotated 50 revolutions. Now if I just rotate a bit, you can see that 0.5 mark is actually appearing here. You can see in the bottom, right? It has appeared now. So when I go to the 0, again exactly 0, this circular edge of this circular division is exactly on the 0.5 division, 0.5 mark division. That means the pitch of this one is a very important thing. Pitch of the screw that we have used here is actually equal to 0.5 millimeters. All right. Now the least count. So the least count is the distance moved by the spindle. This is spindle, no? Distance moved by the spindle when you rotate a single division of the circular scale. This is called the, you can see I have turned one division. This is the lowest measurement that we can take, right? When I just rotate a single division, so you cannot actually see the movement of this spindle, but it has actually moved a very small distance. It has moved. So that distance is called the least count of the instrument. So how do you calculate the least count of the instrument? So when I rotate 50 divisions, it moves 0.5 millimeters. Then if I rotate only one division, then how many millimeters, right? So we can easily calculate the least count. Least count is equal to, if I move the circular scale by 50 division, it will move 0.5 millimeters. So I need to find the distance moved per one division. Then what I have to do is I have to divide 0.5 by 50 millimeters. So you can get the answer as 0.01 millimeters. So you can see this has a very smaller least count. That means the accuracy of this instrument is very much greater than the vernier scale. So micrometer screw gauge accuracy is greater than the vernier caliper accuracy. Right. I hope this is clear. Right. Then actually, if you generalize this formula, least count formula, you can write down the generalized formula as least count is equal to this 0.5 millimeters means the pitch of the instrument. So you can write down pitch divided by this 50 is, what do you mean by this 50? 50 is the number of divisions in circular scale. So you can write down number of divisions in circular scale. So this is the actually the formula for least count of the instrument. Right. So this is one of the most important things that we need to understand, how to calculate the least count of the micrometer screw gauge. Right. Now let's see, if you know the least count, how do we read the micrometer screw gauge? So I will use this same module because the same example, the same simulator, then it is actually very easy to tell how to read this one. Okay. So let's go one by one. So let's first we'll get the reading methodology, how to read this one. First we get that one. So let me erase this one, and this one. Right. Okay. So the reading is actually, this is read similar to the vernier caliper. So that means first what you have to do is, first you have to take the main scale reading. First you take the main scale reading. Then you have to add I will take it somewhere here. You have to add least count multiplied by number of circular scale divisions. Least count multiplied by number of circular scale divisions. Number of circular scale divisions. So this is how you read the micrometer screw gauge, right? So you just need to keep this in mind. This is similar to the vernier caliper. We have done a lot of examples last week regarding the vernier caliper. The same procedure you can follow. Rather than saying the number of divisions coincide with the main scale, like in vernier caliper, here you have to get the number of divisions or number of circular scale divisions coinciding with the main axis of the main scale. Main axis of the main scale, right? Okay. Now let's see, we will read some we will read some values. Okay. Oh, right. So let's say I am moving this one to this side and I am randomly stopping this one somewhere. So what we have to do is we have to read this one. What is the reading of this one? Let's say I am stopping somewhere here. A random stoppage. I did a random stoppage. Now we have to read this one. Now we will carefully look at the what is the main scale reading. So if you go here it is the 5th millimeter mark, then 6, 7, 8, and 9. So now you are checking actually the edge of the micrometer screw gauge, right? You are checking where which main scale division is passed by the micrometer screw gauge edge. So this is the edge of the micrometer screw gauge, and what is the main scale division it has passed. So if you see clearly, you can see that 6, 7, 8, and 9 millimeter is the one which has been already passed. So the main scale reading is 9. So you have to write 9 plus. So we have already found the least count of this instrument, that is 0.01 millimeters. Then you have to multiply this one by the number of the circular scale divisions coinciding with the main scale, main axis. So you have the middle axis here. So if you look carefully, you can see this is 35 and the mark above that means 36. 36 is exactly coinciding with the main scale, main axis. Therefore, you have to multiply this one by 36. So it will give you 9 plus 0.36. So that is equal to 9.36 millimeters. So this is our first reading. I hope this is clear how to take. This is not actually difficult. This is very easy, but we have to be very careful when we are taking the what we call the main scale reading. Okay, we'll try another example quickly. So I will keep turn this one and I will randomly stop that, right? Okay, so we'll turn the bit or somewhere here. Okay, I will stop. Now, let's see how to read this one. Now, if you check here, what is the main scale reading? So you can see 5, 6, 7, and you also can see the bottom one. Bottom line also visible. So bottom line means 0.5 mark. That means 6, 7, and 7.5. So it has actually turned up to 7.5. So the main scale reading will be 7.5 millimeters plus, you have to put the least count, 0.01 multiplied by the main scale, number of circular scale divisions. So if you see here, you can clearly see that is 41. 41. Therefore, you have to take the summation of these two, 7.5 plus 0.41, which will finally give you 7.91. Therefore, the reading is 7.91 millimeters. Right. I hope the reading is very clear. How to read this one? Not difficult if you clearly understood this one. Right. Then we will move to some examples of the readings. Right. Right. So these are the examples. So I encourage you to do this one by yourself. So for the first four, I will give you a few minutes for you to try this first four. If there are no any errors or something is not available yet because we didn't discuss about that one. So you just try to complete these four questions. Okay, now you can start. Take 1 or 2 minutes and we can do this one. Okay. So most of you have sent me the answers. So let's check one by one, right? Okay. So if you go to the first one, you first look at the main scale reading. So you can see clearly it is 11, 10, and it is 12, right? Therefore, the main scale is 12. I will type it here. 12 plus, so this is basically the least count is 0.01 and it should be multiplied by the number of divisions coinciding with the main scale. So that is 15, 16, 17 and 18. Therefore, your answer will be, you can directly write down 12.18 millimeters. Right, good. Next, we will go to the second one. So if you see here, the main scale reading will be 5, 6, 7, 8 and 9. 9 plus 0.01 multiplied by the number of division, that is actually 49. So your final answer will be 9.49 millimeters. Now if you go to the C1, so here the main scale reading will be 10, 11 and 11.5. Be careful, there's a 0.5 mark also. 0.01 multiplied by 45, 46, 47 and 48. Therefore, your answer must be 11.98 millimeters. If you go to this one, D, you can see here 11, 12 and 12.5, right? And you can see here 12.5 plus 0.01 multiplied by, now you can see it is 0. Right? If it is 0, then your answer must be exactly 12.5. But you can see this has been moved greater than 12.5. That means this is not actually the 0. It means it is 50. Because 50th mark and 0th mark is at the same point. Right? Therefore, this is not actually 0. This is actually the 50th, because if this is 0, then your answer must be exactly 12.5. It is that mark. But you can see that the micrometer screw gauge edge has moved to the right hand side. Right? Therefore, this must be 50, not 0. Therefore, your answer will be 13.00 millimeters. Your answer must be with 2 decimal points. It is a must. Okay, because the accuracy of this one is up to 2 decimal points. Therefore, you have to put the answer into 2 decimal points also. Right. So I've got a few answers, right? Yes. So someone have some of the you have actually put that is as 0. Then it is wrong, right? And some of you have missed to get 11.5 as the main scale reading in question number C. right? Okay. So if you have done any mistakes, please correct them. Right. Now we'll move to the next few examples. Now, if I have any mistakes done here, right? Now try to correct them in the following examples. Okay. Now you try to do these 4 examples without getting wrong. Okay. Now you can do this one. So try to do this one now. If you go to the question number G, so you can see the main scale reading. That is basically 13.5. Therefore, 13.5 plus 0.01 multiplied by 31. Right. Therefore, you can see here that is 13.81 millimeters. Those who have got this correct, very good. Then if you go to the question number H, you can see here the main scale reading is 1, 2, 3, and you have a small mark here that is 3.5. 3.5 plus 0.01 multiplied by 35. Therefore, it will be 3.85. Millimeters, right? If you go to this one, I. So the main scale reading is, you can see here, it has already plus 5.5, and if you clearly see, so it has actually moved a 1 division. If it is 0, that means it is exactly at the 6th division. That means 6 millimeter mark, because it has already passed 5.5 and it has passed to 0 also. It has passed 0 also. So we checked earlier, if this one has passed up to 0, that means that is not actually 0, it is the 50th division. That means it has completely gone another 0.5 millimeters. That means the mark here will be the 6th millimeter, right? Therefore, the main scale division is 6 plus 0.01 multiplied by 1. That is 6.01 millimeters. That is why actually it is very difficult to see the 6th millimeter mark here. That's why then you have to consider from this side, right? Okay. Now if you go to here, you can see the main scale is 12 plus 0.01 multiplied by completely 0. So it cannot be 0. No. If it is 0, it should be exactly 12. If it is exactly 12, it must be coinciding this with this mark, right? With this mark. But it is not coinciding with that mark. But the 0 is located here. So it must be not 0, it must be 50. Therefore, it should be multiplied by 50. So that is equal to 12.50 millimeters. So those who have get this one correct, very good. Okay, we have correct answers. And for fourth one, I think most of you have mistaken as 3.51, but it should not be like that. Because of that, complete 50 divisions rotation, not only one day, not the 0, but completely 50, right? There you have to be very careful, and we have correct answers also. Very good, very good. And those who have tried, very good. If you have done the mistake, don't worry. Please correct it this time rather than waiting for the last minute, right? Okay, good. Now let's move to the systematic errors associated with the micrometer screw gauges. What are the systematic errors associated with the micrometer screw gauges? So like in the vernier caliper, we have two kinds of possible errors in micrometers also, right? So actually they are right here. So these are also labeled as positive zero error and negative zero error. So how to identify whether there's a zero or not? Let's check how to identify that. When the end of the screw and the surface of the stud are in contact with each other, the linear scale and the circular scale reading should be zero. That means if I use the virtual micrometer screw gauge to demonstrate that one, so what you have to do is you have to rotate this one in this direction until the anvil and its spindle touch each other. So rotate like that until the anvil and the spindle touching each other. I will rotate faster. These simulations are free and you can see them actually. This is very good. So there you can understand what is actually happening here. Okay. Now you can see now. Do you hear some sound? Tick, tick, tack sound. Can you hear that one? Right. So in this simulator also you are getting a tick, tick sound. When you come to here, when you still try to rotate this one, right? It is giving a tick, tick sound. That means you cannot turn furthermore because this anvil and spindle is already in contact with each other. So you cannot move this anvil more forward. Right. Now if you see here, you can clearly see the half of the zeroth mark is visible here. That means exactly this edge of the micrometer screw gauge is located on the zero line. So if I turn to the other side, you can see this is the zero line. You can see when it is turned to the maximum to this side, you can see the zeroth mark of the circular scale is exactly aligning with the main axis. That means this micrometer screw gauge is free from any systematic errors. There are no any errors. But there are micrometer screw gauges where even though the spindle and the anvil are touched each other, they are not showing the zero values. They are showing some different values. So for examples, in this diagram, you can see these three are enlarged micrometer screw gauges. You can see in the first diagram, the zeroth marks are exactly coinciding, right? They are all exactly coinciding. That means there are no any errors associated with this micrometer. But if you go here, you can see here, even the edge of the circular scale is located on the zeroth mark. You can see here, the zero of the circular scale is not coinciding with the main axis of the main scale. That means this is having some kind of error. If you go to the third one also, there also you can see zero mark and the zero mark of circular scale are not coinciding. Therefore, this one also must have an error. Right. If you see the difference between this one and this one, what will be the main difference? So here what has happened is, you can rotate more actually. You have to rotate some more amount to bring this one to 0. That means this has been come to 0 much earlier. The second diagram, micrometer screw gauge, has come to 0 or come to the edge of the scale, or the minimum reading has achieved the minimum reading even before the 0 mark of the circular scale reach the main axis. So if you try to turn this two more divisions, if you somehow turn this on two more divisions, then this will become free of errors. But the issue is this has been stopped earlier. When you are rotating like this, you have to rotate like this, no? So it is, you have to tight this one. So let's say this is that micrometer part. So if I show it closely, so here there is also thread is there. So you have to rotate like this. In this direction, you have to rotate. So when you rotate this one, what has happened is it has stopped earlier, right? You have to rotate two more divisions to bring that one to 0, but you cannot because the spindle and the anvil is now already touching each other, right? So it is actually stopping earlier. So this early stops we called as positive 0 errors, right? If your micrometer screw gauge is showing an earlier stop, then it is called a positive 0 error, right? Similarly, now in this one, what has happened is this has been turned more. This one is not turned more, this one is turned more, right? So that means this one is having a negative 0 error. If the 0 of the main circular scale has stopped earlier or before the main scale 0, we call it positive 0 error. If the 0 of the main circular scale has passed the main scale line, then we call it a negative 0 error, right? So if not, you can remember like this one also actually, but you have to be very careful when we are going for the shortcuts. I do not recommend to go for shortcuts, but this is the shortcut method also. If the main scale 0 is here and the circular scale 0 is below the main scale 0, below, then it is called a positive 0 error. If your main scale is here and the circular scale 0 is above the main scale 0, then we call it a negative 0 error. Below the main scale, we call it a positive 0 error. Above the main scale, we call it a negative 0 error. But it is better if you can remember not like that button as early stop and post stop, right? This has been early stopped. This has been post stopped. Already turned more. Okay. According to the figure B, the 0 error, the gap between main scale line and the 0 of the circular scale is 0.03. So if you go here, you have to calculate the distance from here to here. So it is actually not 0.03. This value is wrong. We have to correct this one. This is the mark which is coinciding with the main scale. Now you count to the downwards where the 0 of the circular scale is located. Then there are two divisions. That means 0.01 multiplied by 2. Therefore, the 0 error of this one is plus 0.02 millimeters. Right? Now, if you go to here, you can see here clearly it has got one division more. Therefore, this one has a negative 0 error and it should be 0.01 because only one division is rotated in the upstream. Right. Okay, according to the figure C, the 0 error of the scale. So you have given the same description there, how to get that one. Right. Okay. Now let's see what are the 0 errors of the following micrometer screw gauges. Whether it is positive 0 error or a negative 0 error. Okay. Now I will show you how to do the first question. Then you can continue with the other questions. Right. If you go to the first question, now you can see here, this has been early stop because we have to rotate this one furthermore to bring the 0 mark of the circular scale to the main scale 0 mark. You have to further rotate this one like this way. You have to further rotate like this way. Then only it will come here. You can use this principle also, this right hand principle also. We use this right hand principle. So you have to turn, you have to move the micrometer to this direction, left hand direction, edge of the circular scale, you have to move to the left hand direction. Then you have to turn like this. So when you are turning like this, it has stopped earlier. How many divisions earlier? 1, 2, 3. 3 divisions earlier. Therefore, your 0 error value is plus 0.01 multiplied by 3. That is 0.03 millimeters. This is the answer of that one. Now, you can use the same methodology, the same way that you read the micrometer screw gauge readings, you can get the 0 errors of the others also. Right. Now it's time for you to do this one. So quickly try to get the 0 errors of these micrometer screw gauges. So you have 4 examples to complete. Okay. Quickly start and do that one. Okay. Now if you go to here, the first one we have discussed and the second one. Let's discuss the second one. So here also you can see the main scale 0 is not yet reached. Right? So if you rotate more, then only it will come to here. And you can see the line of the 0 mark also. That means it has been stopped bit earlier. Right. Therefore, if you go here, what should be the main scale reading? That is 0 actually. So you have to multiply 0.01 multiplied by the number of division is actually how much divisions? The variation is how much divisions? We have to rotate more. So this is 16th one. 15, 16. Therefore, you have to rotate this one 60 divisions more to bring 0 to here. Right? Then only you can make coincide 0 and 0. Right? Therefore, you have to rotate the 16 turns, that 16 divisions. That means the error is, it is pre-stop. Right? That means a positive 0 error and the value is 0.16 millimeters. This is the 615, this is 16th, right? Okay. Now if you go to here, the C1, so you can see here, 0 of the main scale is located somewhere here, and you can clearly see that it has overturned now. That means it has been, the 0 of the circular scale has already passed the main scale 0. So definitely this should be a negative 0 error. And how many divisions? 1, 2, and 3 divisions. So it should be negative 0.01 multiplied by 3. That means negative 0.03 millimeters. That is for C. If you go to the D one, you can again see here clearly it has been pre-stopped. So you have to rotate this amount of divisions to bring this 0 to here. That means 0.01 multiplied by how many divisions to rotate to be get to 0? 1, 2, 3, and 4. Therefore, this is a positive 0 error, that is 0.04 millimeters. So all these positive 0 errors that you have get must be reduced from the final reading. That is why actually it is called a positive 0 error. All the negative 0 errors that you have obtained must be added to the final reading to make it correct. All the positive must be reduced, all the negatives must be added. Right. Let's move to the next one. Okay, quickly try this one. Just take 2 to 3 minutes and complete this one. So I can skip these examples and go, but that is useless actually, because there are some important examples here. That's why I'm asking you to do this one. Okay, please try to do this one with that time, with it given time. Okay, quickly do this one now. Right. So if you go to here, this one, I hope I showed you E and F also, but if not, sorry. But however, I will go with these two also, E and F also. Right. So if you go to here, you can see here, 0 is completely visible to us. And you have 0 here. So what does that mean is, this has been rotated, the circular scale has been rotated one complete rotation, then only you can see this one. That means you have to rotate this circular scale one complete revolution, then only you can have 50 divisions, right? So this has been stopped one rotation earlier, right? Therefore, this has been a previous stop. Pre-stop. That means it should be a positive 0 error. That means 0.01 has to be multiplied by, here the number of divisions should be 50, not the 0. Then 0.50 millimeters is the 0 error of this one. Right? Okay, if you go to here to get the 0 error of this one, sorry, I have turned off the camera. Okay, then if I go to here to get the 0 error, so what will be the 0 error here? So here the main scale division, you cannot see actually 0. That means this has been overturned, turned more into the main scale 0. So how many divisions it has been turned more? So this one is actually 40, 41, 42, 43 and 44 divisions. It has been here. So how many divisions away from actually 50? So what is the difference between this point and 0th mark? The 0th mark will be located somewhere in the top, right? So you know that if it is 45, 46, 47, 48, 49 and 50. So there are how many divisions? 6 divisions are there, right? 44 to 50 means 6 divisions are there. Therefore, this has been moved 6 divisions more towards the 0. Therefore, the zero error must be -1, 0.01, and it should be multiplied by 6. Therefore, negative 0.06 millimeters is the zero error. Right. Now, if you go to the G1, so you can see here also, if you clearly see this one, 0 is not visible to you. That means this has been overturned. Therefore, it must be a negative zero error. Now, this is the 31st division. This is the 31st division. So, how many divisions it has been overturned? So, 50 will be located in the top side. That means the 50 means actually the 0th mark. So, how many divisions it has been overturned? 19 divisions, right? This is 31, then 41, 10, and 9. Therefore, it has been turned to 19 divisions more. Therefore, 0.01 multiplied by 19. That is equal to minus 0.19 millimeters. This is the zero error of G. Now, if you go to zero error of H, you can see here, you cannot completely see zero. That means definitely this should be a negative zero error because this has been overturned. Therefore, minus how many divisions? Only one division. See here. Only one division, there's a difference. Therefore, the error is 0.01 millimeters. Right. So let's move to the bottom ones. So if you go here, the last two we'll quickly do. So here also you can clearly see that it has been overturned. The zero is not visible here. That means overturned. That means a negative zero error. How much overturned? This is 35, 36, 37. The division is here. And it has been overturned by 13 divisions. Therefore, the zero error is 0.1 multiplied by 13, which will give you minus 0.13 millimeters. 0.13 millimeters. Right. Now, if you go here for the final one, here you can see that you can clearly see the zero mark. So what does that mean actually is, that means it has been pre-stopped. This has been stopped pre, that means earlier. This has been stopped earlier. So you have to turn more. So how many divisions that you have to turn this one to bring to the zero? This is very tricky one. Okay. So you are not turning into this direction. You are not turning back. So you have to turn completely a cycle. Right. That means you have to turn another 48 divisions to bring this one to the zero. Therefore, the error of this one is positive because it has been pre-stopped. And how many divisions you need to rotate this one in this direction? How many rotations that you need to do is actually 48 divisions. You have to rotate this one. Right, you have to rotate this one 48 divisions. Right. Then only you can reach the zero error. Therefore, actually this one is 0.48 millimeters, and it should be a positive zero error. But I hope these examples are clear. If you have any doubts regarding this one, please raise the questions. Right. Then, to how to determine the correct reading. So in these examples, I have actually given the what is the value of the zero error. So you have to eliminate the positive zero error, you have to reduce the value. To eliminate the negative zero error, you have to add the value. That is what you have to do, right? So in all the examples, I have already given the zero error value. So you have to write down the actual reading. Okay. So let's start with the first four, A, B, C, D. So like earlier, I will give you 2-3 minutes. Please try this one. This is important because today also I will show you the A-level examination question examples from this one. Right? Okay. Quickly do this one now. Now, if you go to the question G, then we can write the main scale reading first. What is the main scale reading here? If I write from here, the main scale is 11 and 11.5. 11.5 plus 0.01 multiplied by 20, and then it is 18. So you can get this one as 11 point, we have 1.8 there here, 6.8. 6.8 millimeters is the given reading, and then you have to correct that one. So the corrected reading will be, you have to reduce 0.37 from there. 11.68 minus 0.37. So that is actually 11.31 millimeters. If you go to this one, then what is the main scale reading? You can see here 6, 7, and here also you can see it has been only 4. That means in order to get 4, first you have to pass 0. So it must be, it has not reached yet the 8th mark, but you can, if you see from the bottom, it has just passed the 7.5 mark. So the main scale reading is 7.5, and you have to add 0.01 multiplied by 4. Therefore, the final answer is 7.54, and then we have to add 0.16 for this one. 7.54 plus 0.16. So this will give you 54 plus 16, 64, 70, 7.70 millimeters. Right. If you go to question number I here, so you can see it is the main scale reading. You can see here it is 1, 2, is 12, and it is again completely 0. That means the main scale reading must be 12.5 plus 0.01 multiplied by, there are no any divisions passed, it is exactly 12.50. So you can neglect that one, and what you have to do is you have to reduce 0.11 to get the corrected reading. Therefore, what is the answer? 39. So if I 12.39 millimeters. If you go to here, the main scale reading will be only 1 millimeter has passed, plus 0.01 multiplied by 26, that is 1.26, and you have to add 0.49. 1.26 plus 0.49. This one should be equal right here. It's not changing. Okay, not sure. You write this two. Therefore, how much is that? 5, 6, sorry, 7, 1.75. So these are the corrected readings of these examples. I hope you have with me and you have completed the examples before I do also. Right. Now, if you have any questions regarding the examples that we have discussed, please raise. Okay. So this is what we have to discuss about the micrometer screw gauge. This is how to take the reading. This is how to take the zero error. This is how to calculate the least count. Then now you know how to manage, how to use two measuring instruments. So the actually first one is a vernier caliper. Second one is micrometer screw gauge, which is the accurate one, even greater than the micrometer screw gauge. Right. So, but both of these equipments has one constraint. So that constraint is each and every time that you are taking the measurement, you have to keep the object in between two parts. In the vernier caliper, you had external jaws or the internal jaws, and you have to tie it. And here we have anvil and the spindle. Then also you have to tight the object in between these two components. So if you do not have a rigid body like a metal ball or a stone or plastic, hard plastic, then you cannot actually measure. If you don't have something like that, right? If you have a rubber ball, if you have a balloon, right? If you have flexible material, then there's a problem when you are using these kinds of instruments. So it is not possible for you to measure. Because when you tight the instrument to keep them in between the jaws, the object will deform. Then you cannot take the measurement. To avoid this error and to take measurements, there's a special equipment that we can use in such situations. So it is called as the traveling microscope. It is called traveling microscope. Okay, so this is the instrument that we call the traveling instrument. So it is a bit complex than all the other instruments. This is a bit complex, right? Okay, so first we will learn what are the parts of the uh, traveling microscope. Then we will discuss about the use of every part. Okay, so actually we have a question. So because this part is not mentioned in the tutorial, right? So this is actually I think the total part is not available, I think, right? So you will receive that tutorial because actually during the posting of the tutorial, this tut has been missed from my side. Actually, I haven't been able to give this one, right? So extremely sorry for that one. So in the next uh, tutorial setup that you are going to get, you will receive this one. Until that one, so I will share this one with our team lead, and then it will be shared with you, right? So the PDF I will give you after discussing, right? So uh, so first focus on what I say, right? Then I will share the document, because I know if I share the document first, what will you do is you will not focus actually, right? Because you know you have the document, then you don't need to look at. So this may happen to the other instrument, right? This spirometer, I know definitely that will happen to you. So you only did the examples when I say, because you only see at this moment. That's why you actually did this one. If you had the tutorial, I know you will think, I will do it later. I can do it later like that. So, however, don't worry about that one. You will receive the tutorial. So that is a mistake from my side. So until that one, I will share you the PDF document. Then you can go through. So I will put this one into the WhatsApp channel, right? Then you can go through. So today I will put after the class, I will definitely share it with you. So let me check if there's any possibility that I can attach here, then I can directly attach here. Let me check. So I think I can, let me attach there. Right. So this microscope is actually a bit complex instrument that we have. I think this is the most complex one, I think. Right? So let's go one by one. Let's understand what are these components, and we will try to watch a simulation of this one. Right? Okay. So if in the name also it is given that it's a microscope. So definitely then it should have a microscope. So where this microscope is located? So I think all of you have seen microscope. So what is the use of a microscope? So microscope is used to see smaller things uh, with more clarity, right? To basically to see small things. So like microorganisms you can see, so cells you can see like that way. Now imagine you have very small distance to be measured, right? So that is very small such that you cannot even keep your vernier caliper or the micrometer screw gauge, right? And just imagine you have a rubber tube, rubber band. Just imagine rubber band, a small rubber band is with you and you need to measure the thickness of that rubber band. So you can use you can try with the vernier caliper but when you squeeze it between the jaws, it is deformed, right? Now, if you imagine a rubber tube, like a saline tube, you have seen saline tubes, right? So you need to measure the internal diameter of this saline tube. So if you try to put the vernier caliper, you cannot put because it is too small for a vernier caliper. And you cannot even measure the external diameter because when you keep the saline tube in between the jaws and if you tie it, what happens? It deforms. Same with the micrometer screw gauge. But this is the only way that you can measure that, right? Okay, so this part is called the microscope part. This is the microscope part, right? So in a microscope, there are two main components. So these two components are E and F. In the diagram, the two main components of the microscope are E and F. So this capital E is called the eyepiece. Why do we call it eyepiece? Because this is the place where we keep our eye to look at something, right? Then this F is the objective piece and it is very much closer to the object. So this is pointing to the object. This is the place where we keep our eye. So for your knowledge, keep in mind we will learn about these microscopes later in our lessons. We have optical instrument lesson, so there we will go in detail about the microscope. For now, remember this microscope has two kinds of lenses. So both of these lenses are convex lenses. We call them convex lenses. I hope you have learned about convex lenses in your O levels, right? I hope. If you're not, that's fine. We will learn them in detail in upcoming lessons. So there are two convex lenses. So this piece means what we known as the piece is actually called this lens. Eyepiece means the lens where we keep our eye. Objective piece means the place which is very much closer to the object. So this is the place where, this is the point where we are keeping the object. Right. Now the importance of this microscope is you can actually rotate this microscope unit in this axis. So if you need, this is now right now this is vertically oriented. So if you need, you can rotate this part and take it to the horizontal level. Right? I will try to show you a demonstration of this one. So because it is freely available in the YouTube, right? In YouTube is one of the biggest knowledge sources that you have if you use it correctly. So actually, I do not have a micrometer screw, sorry, a traveling microscope with me because it's a bit expensive instrument, right? So I do not actually possess this traveling microscope. So what I can do is I have actually used in the school time, I have actually used this instrument. So I know what are the components and what are the rotatable parts and not. And the importance is this microscope part is actually rotatable. Now just imagine, I will take these two pens to demonstrate the orientation of this one. So this is that gold color support. So you can see here a gold colored support. So I am considering this blue pen as that gold colored support. And I am taking this black pen as the microscope. So currently it is being fixed to this one by using this one. So I am putting my finger as the fixing point, fixing part. So like that way this is fixed. So the rotatable part is, now this is the objective piece and this is the eyepiece. So this is the place where you keep your eye and look, right? That's why we call it the eyepiece. This part can, this telescope, whole microscope part can be rotated like this. So earlier it was vertical like this, but now you can rotate it like this, right? You can rotate it like this. So you can keep it horizontal. So this is still vertical. It cannot be rotated. It is vertical there, but this microscope, you can turn like that. And you can turn like that. You can turn like that, right? So you can turn. Currently, it is some is vertically like this, and this one is rotated like this. Clear? Okay. So this is that rotating point. So that part is, you don't need to actually remember that part, but eyepiece and objective piece is necessary. Then if you have ever seen through a microscope, you just cannot go and see through a microscope, right? You have to do something. So what do we call that one is, we call it focusing. Okay, so if you have any optical instrument, basically like a telescope or microscope, you must do focusing first. So that means if your object is too much away from your telescope, then you cannot see the object clearly, right? Then what you have to do is you have to focus. You have that experience if you have used a camera, even a phone camera, you have to focus. We are saying generally my phone is not focusing properly. That's why the image is blurred, right? So if this microscope is not focused properly, then what you see will not be clear. It will be blurred. Image will be blurred, right? Therefore, there's a screw, capital D. We call it the focusing screw. A screw for focusing the microscope. So you keep the microscope like this. Now let's say you need to look at the horizontal object. The object is somewhere kept here. So I'm looking through this one, and now we are turning this screw like this. And you can adjust through this one. So until you see clear images, you can adjust by using this capital D screw. Right? So these are the main parts of the microscope part. I'm always saying telescope, sorry for that one. So it is microscope, not telescope, right? So these are the main components of the microscope. Right? Now you have that gold color part, that is the place where the sun has been mounted. So it is actually the vertical support, right? So there is, you can see, if I enlarge this image, you can see there is a ruler. There's a ruler fixed to this one. So this is actually the vertical scale. This gold color one is the vertical scale. You can see here 0, 1, 2, 3, 4, like that way. It's a ruler is mounted to this support, right? And you can see here there's a small scale also. So this is actually a type of vernier. This is a vernier scale, right? Right here is a vernier scale. Right here is the main scale. Okay. Now, if you move to the part B, so part B is the screw to fix the microscope vertically and horizontal. Now, if you keep it like this, then if you, when you are taking the measurement, if this one is getting just like this, a shot from your hand, mistaken shot, then what happens? This one go away, turn away. Then what happens? Then again you have to focus this one. So there must be some locking mechanism. So this B is used to lock this one. So if you make it horizontal, keep it horizontal, you lock from here. Then it is fixed. If you need to take vertically, if you need to look at vertically, then what you do, you turn the microscope vertically, then you lock. So this B is screw to fix the microscope vertically and horizontally, right? Then if you go to C2, this C2 is for the fine adjustment of vertical sliding jaw. So what is that vertical sliding jaw? So this whole part attached to this gold color part, this is like a jaw, like this way. So that is why we call it a jaw. So this is the sliding jaw, right? So this sliding jaw, you can move up and down. So how do you move this up and down? Is by using this C2 screw. Screw for the fine adjustment of the vertical sliding jaw. So this is mean fine adjustment means very small adjustments. So how do you do the large adjustments? That is by using this B. So if you lose this B, then you can move this complete jaw up and down wherever you necessary, right? So by you can lose B, then you can move the whole setup up or down. So you bring that turn to a required point, then you tight it. Now the sliding jaw is fixed. Now if you need to do a very fine adjustment, small millimeter, half a millimeter adjustment, then what you do, you use the C2 screw to do the vertical adjustment, right? Then we have already discussed all these parts. This is the vertical sliding jaw. This is the locking pin, the locking screw. This is the fine adjustment screw for the vertical sliding jaw. This is the eyepiece. This is the focusing screw of the microscope. And F is the objective piece. Right. Next is the bottom part. So this one has this vertical part is mounted on a horizontal base. So this base has two screws. Basically, these two screws is to make it level. So before you are taking any measurement from the traveling microscope, the first thing that you have to do is you have to level the instrument. So have you ever leveled the equipment? Have you ever leveled? If you ever leveled an instrument or leveled anything, if you have seen the mason, we call it mason bars, right? So in order to check whether they are walls, whether the walls are vertical or horizontal, what they use is a spirit level. So that there's a liquid and an air bubble, so they keep it on the horizontal and they check whether the bubble is actually at the center. If it is at the center, then your wall is horizontal. If you keep it vertically, and there's a vertical split also, if they are also, if it is in the middle, then you can say, all right, this wall is completely vertical. So that actually use the help of the gravity. That use the help of gravity. So air is lesser denser, therefore it try to move upwards. If you have any angle, then the air bubble will not be actually at the center. Right? So to make the level, we have two screws, A1 and A2. So A1 and A2 are the leveling screws for leveling the plane of the traveling microscope horizontally. So you need to make this one completely horizontal. For that one, we use this A1 and A2 screws. Okay. So when we are when we are rotating these screws to adjust, we have to look through this leveler. So this is the level. H is the sprit level. So here it is a round one, no straight one, round one. So here you have to bring the small air bubble inside this one exactly to the center of the circle. Then only you can say this is completely leveled. So you don't have 4 screws to adjust. By using only these two, you can do that. Right? So how do you adjust is, you first adjust one and then you adjust the other. Right? Not both at once. You try to adjust one first, then look at this one, then adjust that one. Like that way, you can actually do few times and you can adjust this one quickly. Right. A1 and A2 are used for that. Now H is the spirit level, that is to check the level, horizontal level of the microscope unit. Then this G is actually to fix this vertical unit. So why we need to fix the vertical unit? Because the vertical unit is movable actually. So you can see this C1 screw. The C1 screw says fine adjustment of horizontal sliding jaw. So similar like this vertical sliding jaw, this one is actually fixed to a bar. This bottom part, the black color part, you can see this part is actually placed on this bar. And the importance is you actually can move this one along this section, right? So this is the screw to push this one or to pull this. So if you rotate in some direction, this one will be pushed to here. If you rotate in the other direction, it will be pulled towards here. So you can actually move the complete horizontal unit right and left or back and forth. And there also you can see here also we have placed a scale and you have a vernier scale. That means we actually can move this part horizontally. So we have this part to move the microscope unit vertically up and down. So you can take height measurements. Vertical measurements you can take by using this one, and all the horizontal measurements you can take by using this scale. So actually this is a 2D measuring instrument. You can measure two-dimensional. You can measure two-dimensionally by using this instrument. Right. Okay, so these are the main components of a traveling microscope. So is it important to know these parts? Are they going to ask these questions in the examination? Yes, no one thought that this one will never be asked, right? No one thought that this one will be never. They have asked the micrometer, screw gauge, they have asked the vernier caliper. So most times they have asked that instruments in the A-level examination. They never thought that this much of complex instrument will never be directly asked in a question paper. But what happened is in 2018, they asked this one. They completely given this instrument to identify the parts, right? So if I quickly take you to that question and we'll see whether we can answer that one or not, right? Let me quickly take you there. And papers here. We have the English medium paper, right? Okay, here. Question number 3. Right? The same setup is given, right? The same setup is given. So what they have asked? You are asked to find the refractive index of a glass using a rectangular block of glass and a traveling microscope. So this is another practical that you have to do, right? So here you are given not a question, actually, not a complete question for the traveling microscope, but part of a question. So this instrument is actually using for another practical to find the refractive index that we will learn in the light lesson. So there you have to use the traveling microscope. So they have combined into this one. So you have given this instrument and see what is the first question. Identify the parts marked A, B, C, D and briefly state their functions. So if you go quickly and identify, now you know what is this A? This is the for fine adjustment of vertical sliding jaw. Screw for fine adjustment of vertical sliding jaw. You don't need to write the exact words, but you need to say the idea. So idea of this A is to, so the function of this A is if you rotate this one, you can move the vertical sliding jaw up and down. That is the function of A. Then function of B is to focus this is the focusing screw. The function is to focus the microscope onto the object. That is the function of B. Then function of C, you have two screws here. So what function of C is to level the instrument. Then D, it is the spirit level. You can see here, this is the spirit level. So the function of the spirit level is to check the level of the instrument. Then if only A, B, C, D is asked, but if you go further, this E is used to move the horizontal sliding jaw. Fine adjustment of horizontal sliding jaw. F means the fixing screw. That means when you move the sliding horizontal sliding jaw is some distance, then you fix that part. So that is the function of F. This G means actually the microscope frame. Traveling microscope frame is capital G. And H, you know now, this is the locking screw of the sliding jaw, right? Locking screw of the sliding jaw. And you have the I, that is the microscope. So they didn't have asked about them, they only have asked about A, B, C, D and their function. So they will never ask the complete instrument, but they ask only part and then you have to answer, right? So this is a surprise question surprise question for all, because if you check all the past papers, you can check up to 1980s, you can check, no issue, you will never find this one. But in 2018, then they gave that one as a part of the structured essay question. And this part actually carried the highest marks, right? So that is the importance of paying attention to the lessons and doing the past papers. So they have not asked, actually, those who have done the past papers also won't directly able, but when you do the past papers, you know that this hasn't been asked. So there's a possibility, right? That's why I said, if you do the past papers, then you know what are the instruments that they have already asked and what are the other remaining parts that they can ask. The importance is actually the things not already asked, what is to be asked, right? So those who have actually prepared with this one, they have scored a lot by using this question, right? Now, so we know the uses of this one actually now. So what is the use of this one? So now we will actually go through the statement. Okay, you can highlight when you get the tutorial, you can highlight the important parts. The traveling microscope is shown in figure and its main parts are named. It consists of a base with the main scale calibrated in 0.5 millimeter divisions and a vertical scale calibrated in 0.5 millimeter parts attached to a platform with a vernier scale which can move up and down along the vertical scale. So each of these main scales, you have two scales, main scales, vertical main scale and horizontal main scale. The minimum division, smallest division is 0.5 millimeters. So they have divided 1 millimeter even into two parts. So the divisions are in 0.5 millimeters. And you have a vernier caliper or a vernier scale. Right. A small microscope is attached to this platform and the microscope can be fixed in a horizontal or a vertical position according to the needs. As I mentioned earlier, by using this B screw, you can lock that one in vertical or horizontal position. By moving the horizontal platform along the horizontal scale, microscope can be moved horizontally and the horizontal distance moved can be obtained from the horizontal scale. So you can measure how much horizontal distance it has moved by referring the horizontal scale. Right. By moving the vertical platform up and down along the vertical scale, the microscope can be moved vertically and the vertical distance moved can be obtained from the vertical scale as explained earlier. So you can take the vertical movement distance by using this part. Then tiny movements along the vertical scale can be done by the screw C2. From this one, tiny movements or the fine adjustments of vertical and tiny movements along the horizontal scale done by screw C1. This one. Before using this instrument, the base should be leveled horizontally and that can be done by using the leveling screws A1 and A2. Microscope can be focused on the object of which a measurement has to be taken by adjusting the screw D. This is a microscope adjustment or the focusing screw. The least count of the vertical scale of the traveling microscope is 0.01 millimeters. That is same as the micrometer screw gauge, right? The least count of the vertical scale of the traveling microscope is 0.01 millimeters. The vernier division which coincided with the scale division cannot be read from the naked eye. Therefore, a magnifying glass is used. So these marks are very tiny, right? Because this is marked in 0.5 millimeters. The main scale is marked in 0.5 millimeters and the vernier will be very much smaller. So they are saying that, so actually if you really get this one at your home, you actually cannot read the values properly. Like the coinciding, we have to, when we are taking a reading from a vernier scale, then you have to actually find the what is the coinciding part, the coinciding division. So you cannot take this one from the naked eye because that they are very tiny. Therefore, what have to do? You have to introduce a magnifying glass for that one, right? Traveling microscope is used to obtain measurements such as length of a mercury thread inserted in a capillary tube. So this is one kind of a measurement, right? Capillary tube is a very small tube. For an example, you have tube of the pen. We can say a large capillary tube. So this is your pen. This is actually a capillary tube, a type of capillary tube, but this one is actually a bit larger. There are tubes which are very, very smaller than this. So if you consider a needle where the medicine is injected into your body, so the diameter of that uh, needle, like that kind of thing is called capillary tube, very tiny, right? So this one is also a kind of a capillary tube. So if you need to find the diameter of this one, so very small, you see, it has a very small diameter. So you cannot use either vernier caliper, I mean the internal diameter. You cannot take vernier caliper or the micrometer screw gauge. You have to use the traveling microscope, right? And it is given that traveling microscope is used to obtain the measurements such as length of a mercury thread inserted into a capillary tube. Just imagine this is mercury, this is ink actually, but let's assume this is mercury. So if you need to find the length of this mercury column, then you can focus the microscope first at this point, take the reading, then move it horizontally up to here, then take the reading here, right? I will show how to take the reading. Then you take the difference of the reading. Then you can easily find the mercury column length, like something like that. Because we may need these things in upcoming experiments. That is the problem. That is why we actually learning this one, right? Then horizontal and vertical diameters of capillary tube. Real and apparent depth of mark when viewed through the glass block. So this apparent depth and real depth, that scenario is actually given in the 2018 question paper. Okay, refractive index, calculation of the refractive index, we use that method. For that practical, we need the traveling microscope to find the thicknesses, right? And that means the real depth and the apparent depth. For that one, we have to use a traveling microscope, right? Okay, these are the main usage of traveling microscope. Okay, now if you go to your syllabus, this is your syllabus. So there, what you have to learn. Okay, so it doesn't tell much about the traveling microscope. This is a vernier caliper. Do not have much information, and you have traveling microscope. This is the diagram they have given, and this is the uh, parts. This is the parts actually. So we have a special part here, this one. Some are actually equipped with what you call a magnifying glass. That is actually used to the level. So you can look at the level and you can actually used to read the vernier scale by using this one. So for the vertical one, you don't have a magnifying glass already installed here, but for the vertical scale, for the horizontal scale, you have a installed magnifying glass, very small magnifying glass, but for the vertical, you don't have. Okay, so these are the main components. So this is actually what they can maximum ask, right? So I have included this text actually for your reference. So this is the vernier scale. This kind of vernier scale is actually located in here. We call it the extended. Last time also when we discussed about the vernier scale, I said you about the extended vernier scale. So this kind of vernier scale is actually located there. Right, okay. These are the things need to be that you need to know about the traveling microscope. Right. Okay. Now you can actually do the questions. So if I just show you an example of the past papers, this is 2020, the second question. It is from the micrometer screw gauge. So first you have given a defected one. That means a instrument with a zero error is given in the first diagram, figure A. Then you have given a reading taking micrometer screw gauge. Then you have to find the correct diameter of the metal sphere. Then you have to find the error from this one, and you have to check if that is positive or negative. Then we have to read the microscope here. Then you have to take the final correct diameter. So my advice is to please go through these questions and try to do them. Okay. So answers are not given here. So you do this one first and then you send me the answers. So you can put the question number and your answer. What is your answer? This is MCQs now. So you can easily do this one. So please try to do this one because all of these are possible exam questions. They are not, I don't have very much like 50 questions, 60 questions from this one. This is a limited number of questions only possible, but all these questions are exam standard questions, right? Therefore, please do this one by yourself. Okay, right. Then we can move to the next part of our lesson. That is the tutorial actually that you have, including the spherometer, right? So let me open the tutorial. Then we will start discussing that part. Okay, before moving to this spherometer part, let me quickly take you to the practical guide also, right? Let's go to the practical guide also, then we will check what are the things available in the practical guide. So here you can see the practical guide also. We have the first practical, that is usage of the vernier calipers. They are at the last day also I explain what are the things that they can ask. I show you an example, 2020, 2014 examination paper. And the usage of micrometer screw gauge, we have discussed that one. We have past papers on that one. So I will share them with you. The PDF documents so I have hard copies, so I will convert them into PDF documents and I will share it with you, right? And third one is usage of the spherometer that we have to discuss next, and usage of the traveling microscope. So you see here, 4 of the instruments are already given 4 practicals in the syllabus. That means definitely they can give a question from there, right? So they can actually give mix up and give. So they will not actually give a total question from my instrument. What they do is they use the instrument as a part of the question. As I explained in the 2018 question paper, they didn't give the total question from the traveling microscope. This was a part of the practical. If you have A, B, C, D parts, this is the part A, right? Okay. So if you go here, I will share this document with you. So in this document, you find actually how to use these instruments. So what we discussed last week, external diameter measurement, how to measure the internal diameter, like that, right? Okay. So this practical was actually given in 2014. If you can remember, finding the internal volume of a hollow cylinder. So if you can remember this question that we discussed, they have given something like this, no? Some diagram like this with a hollow. That's what they have given. So they are not actually going out of the syllabus. They are always within the syllabus, and they are giving the questions from this resource book. Even sometimes they will use the same diagram in here. Right. We have seen the tables, you see? Right. And how to read there. It is given 0 errors. But I have explained them in detail rather than even how they have noted in this document. I have gone in detail into how to do the 0 error calculations, how to read, how to find the least count, like that. And for the microscope, screw gauge. So the parts we have already discussed, and how to check whether it has a 0 error or not, how to obtain the least count of the instrument, what do you mean by the pitch, like that way we have discussed almost all the parts, right? So please refer this document also, it's also important. So I have used these diagrams to show the 0 error, right? Then we have this spherometer, so we will move into that turn next, and we have the traveling microscope. Now in this diagram, you can see it, how it is horizontally oriented. You see the microscope is fixed horizontal. And you can see here, in here, actually you have the magnifying glass for the vertical scale. And you have magnifying glass for the uh, horizontal scale also, right? See here, this is the magnifying glass. This is the magnifying glass for the vertical scale. These are the adjusting screws. This is the spirit lever, right? This is the locking screw. The locking is not available somewhere here. So this is the locking screw, right? So the fine adjustment screws are actually not visible here. Okay. Then how to use this one is, now the find in the least count is similar as the vernier scale, because you only have a main scale and a vernier scale. So you can follow the same method to find the least count, the same method that we use for the vernier caliper, because we have vernier calipers here, main scale and a vernier caliper. And then this is how the measurements are taken. Just imagine you need to take the internal diameter of this is a glass tube, something like I showed you the internal diameter of your ink pen, ink tube of your pen, right? So it has some thickness like this, and you have to measure the internal diameter. Right. Now see the technique that we use. Now, this is a microscope, no? So when you see through the microscope, you can see a very enlarged image. So when you are looking at this image, actually you can see crosshairs. What do you mean by crosshair? So let me draw a crosshair and show you. So I will use this space to draw a crosshair. This space I will use. So you actually know what is a crosshair, but I will draw and show you. So if this is the seeing area, if you keep your eye on the eyepiece, this is your scene area. You can see a circular disc. Okay, you can see a circular light spot. So through that light spot, you can see. All right. So the crosshairs is like this. So it has divided into two parts like this. There's a vertical crosshair and a horizontal crosshair. So it is like a target, no? You know that when you are doing targeting, this is how. In a gun also, this same targeting is used, right? So this exact center is here. Intersection point is the exact center. So it is like a target, right? Targeting mechanism. You call them crosshairs. We call them crosshairs. If you see through the eyepiece, you can see these crosshairs. So if you don't see these crosshairs, that means you haven't adjusted the microscope properly. If you using that screw adjustment, you have to turn the screw and you have to adjust that one such that you can see the crosshairs clearly. You should be able to see the crosshairs clearly. Okay. Now, what is this use of this crosshairs is, this is the use. Now, what you do is, you look at through this one. Okay, so if this is your objective piece, this is your eyepiece. Just imagine this is your eyepiece and this is your objective piece. Now you hold the tube in front of this one. You hold the tube in front of this one, like facing to the microscope directly, like this way. So let's assume this is your microscope. This is your microscope, right? This is your object to be measured. So what you do is, so this is also already mounted to the support, and what you do is you take another support and mount it in the directly in front of the microscope, right? Like this way. You have to mount like this. So you have to take external mount like this, and you have to keep it like that. Don't try to hold this one. Okay, when we are vibrate, if your hand vibrates like this, then you will never be able to take the measure. Therefore, you have to use a hard, non-moving, non-vibrating, stiff stand. So you have almost a stand, very good stands in your laboratories, right? To hold the test tubes like that way, you have the stand. So you put this one on a stand and you clamp it such that it is not moving. Then what you have to do is, then you have to see through the eyepiece like this way, and you have to take the crosshairs to these positions carefully. So first take your crosshairs at to this point, right? Then what you do is you take the measurement of the horizontal vernier scale, right? You take the horizontal measurement of the vernier scale. You just write down the reading. Then you have to move this crosshair to here, directly to the other side without moving up and down, because now you have fixed this one in the vertical scale. You know that definitely this one is not moving up and down. Now the microscope is not moving up and down, so you can move this one up here and back and forth only. So what you do is, first keep the crosshairs at this point like this way, looking through the eyepiece of the microscope. Take the crosshairs to this point and write down the measurement. Let's call it x1. Then you move the microscope horizontally by using the C2 screw. If you can remember in the diagram, so this one, sorry. This one, C1 screw. You can turn this C1 screw and you can move the crosshairs to here. Then you note down the reading. That is x2. Right. Now there's a very special thing about this microscope. If you ever see through a microscope, right, you will notice that the images that you see are inverted. Right? Images that you see through a microscope are always inverted. If you look at an arrow which is in upward direction, when you look at through the microscope, you will see an inverted one. Always in a microscope, you will get an inverted image. Right. Because of that one, let's assume first you focus to this point. Then you need to move this one to this point. The crosshairs need to be moved from here to here. So the crosshair movement is to the right hand direction. So if I asked to what direction that you should move the traveling microscope. So since this is inverted image, then if you need to take the crosshairs from left to right, then you have to move the traveling microscope from right to left. Right to left. So in the red color, I am showing the direction of the microscope. Direction of microscope. So sometimes these may not be in the tutorial, right? Therefore, please take notes in your notebooks. This is important. Don't just listen. Try to take something down. Right? In the tutorial, they will be there, but sometimes some things may not be there. So sometimes you need to actually practically see things. So at the moment, we cannot practically see. That's why I am actually telling. So direction of the microscope is to the left, then the crosshairs will be moved to the right side because of the lateral inversion. Lateral inversion that you see in a microscope. You will learn about that. So in a microscope, up and down will change, right and left will change. That is called the lateral inversion. Is the right left change, and up and down change is called the inversion. Right. So similarly, in here also, in the other one also, your next measurement is, so you take a horizontal diameter. You need to measure the diameter of this one. So you measure the horizontal diameter. The difference of these two measurements give you the separation distance between these 2 points. Right? That is called the horizontal diameter. Now you need to take the vertical diameter. So you keep the crosshair somewhere here. Let's say this one. So you focus the crosshair to this point and you take the reading from the vertical scale. So this Y1 reading is taken from the vertical scale. Then you need to take this crosshairs to the downwards. So if you need to take the crosshairs down, to which direction you have to move the sliding jaw, vertical sliding jaw? You have to move towards the up. So using the fine adjustment screw in the top here, this is screw, C2 screw, you can move the sliding jaw up. Then the crosshair will be coming down. That is because of the inversion, image inversion, right? So you have the two readings now. Then you take the separation. Then you have the horizontal vertical diameter. You have calculated the horizontal diameter. You have calculated vertical diameter. So you can add these two values and take the mean value. That will be your diameter. That will be your diameter, right? Taking the mean value. So we discussed that to remove the random error, what you can do is take 2 measurements or 3 measurements and take the mean value. So here what we are doing is actually removing the random errors, right? Or any abnormalities or any unevenness in the tube. That also can be removed by taking 2 measurements and taking the average. Then if you go to here this is a rubber tube and we have to measure the thickness of this rubber tube. And that means internal diameter and external diameter, right here. So the similar way you can measure. So crosshairs, if you need to move the cross, you have to start from one side and you have to take measurements here, 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 and here. In here also, you can take the internal diameter first, then external diameter, internal diameter, external diameter. So separation between external diameter and internal diameter will give you 2 times the thickness. Here also 2 times the thickness. Then finally you can take the average and you can find the thickness of the tube. So that these are very simple values. After you are taking these values, then the rest of the Calculation part is simple actually. Taking the measurement is the difficult part. Right. So you can see here how the method is given. First, determine the least count of the traveling microscope and note it down. This is the first step for experiment. So when someone is asked what is your first step when you have given a instrument, there I mentioned last week also that must be what? Finding the least count. That is the first thing. Then fix the capillary tube to coaxially with the microscope. Coaxially means in the same axis as I mentioned, coaxially. With the microscope part of the instrument on the stand and focus face of the capillary tube by the microscope face to face there. You have to keep it face to face. And you have to keep a stand. Use stand for that part. Then move the microscope horizontally until the crosshairs of the microscope get adjusted as shown in figure 4.2. Right? You can read that one easily. Using the horizontal scale, observe the reading x1 and x2. Next, move the microscope vertically, like that way. Remove the capillary tube, insert a rubber tube. Then, when you need to measure when you take the measurement of a rubber tube, then you have to remove the capillary tube and then put the rubber tube there. That is just practical, right? So you have the table, you take the values, you take the internal diameter mean value, you may take the mean internal diameter of rubber tube, right? Okay. So like that way you can take mean values. Here you can see there's difference divided by 2. So these are the values. So the most important part is the conclusion part. Record your conclusion in accordance with the above calculations. Right? You have to put a conclusion on that part. Present your opinion about the above conclusions and their errors, and also suggest your suggestion about the obtain these values accurately. What are the other possible values to obtain these values accurately? Right? Right. So these parts you have to write down actually when you are doing the practical. So please do the practicals in your schools. If you are going to school, that is important. If let's say assume someone is not going to school, then they can do these experiments. So I'm saying use the most frequent energy source. Sorry, what we call energy source, actually study source actually. So that is you can use the YouTube. So there are a lot of videos that has been done on this microscope experiment. Right. I will also share some links also. You can actually go into them and do. But the best way to learn this one is to actually do. So if you are going to the school, please touch this instrument, use this instrument, try to turn it up, down. You try to look through the IPs, you check what are the movable parts of the instrument, how to adjust, how to tighten this one, like that. Please do those things because these are the things that they actually trying to get from you in the examination. So you have a note here. Use a rubber tube of 5 centimeters or 5 millimeter diameter. Insert into the tube a cylindrical piece of wood slightly smaller diameter than the rubber tube to facilitate the fixing of the horizontal tube. This is how do you fix a rubber tube actually. Like a saline tube, if you need to fix a saline tube to a stand, then it is actually not hard, no? Then it is like that way, right? So you need to keep it like this way. So you know, keep it like this way. You can put a small wood piece into this one, right? Then it will be somewhat rigid. Then you can actually keep it like that way. If not, you cannot actually fix something like a rubber directly in front of the microscope because it will deform or it will slag like that. So to keep it like this rigid, then you insert some wood piece into that. So that's how it is given that. So these things are actually learning from the book is not much efficient. So these things are practical. So when you are doing the practical, if someone is asked to find the diameter of this rubber tube, then you will understand that you cannot fix this as mentioned in the class, right? So you need some other mechanism to fix this one. These are the things actually that the examiners are checking. whether you are practical, whether you're a practical person or not. So if you're a practical person, if you can think this is how to fix a rubber tube, then they actually accept. If you have given any method to fix this, or any acceptable method, then they will accept the answer, right? So try to think of these practicals, try to see some videos of the practical. You can actually search. If someone required, please let me know, then I can share you the links of that one, so you can go and learn by yourself. So I'm here to explain the fundamentals and basics, and I will actually go according to the syllabus. But if you need to understand more, then you have to do some self-search. That part you have to do, right? Okay. So these are this is all about the traveling microscope. I hope I covered everything about the traveling microscope with that one. So we have only one instrument remaining. So next week we will complete the spherometer. We will not take much time on that one. And after that one, we will move to the interesting, one of the interesting part of our lesson. So what is that? So what are the things that we have to discuss under this lesson? So if you go to your, we call it the resource book. So there, you can actually read something about the spherometer, right? Then we have actually a time measuring instrument that is not much. We don't need much discuss about these measuring instruments that we already. This one is also not much important. This is called the mass measurement. We call this a triple beam balance. This is also not that much important one rather than the vernier caliper. Not much, because actually to measure the masses, we actually do not need this one now. We have digital scales. You can put directly and use the digital scale. That is accepted in examination also. A digital scale or electronic scale is accepted as an answer to measure the mass. So you don't need to do much trouble putting the masses, hanging the masses somewhere here and taking the measurement. That is not actually much required, right? You have sophisticated technology like this. You see, we have a directly electronic scale. You can directly read. Actually, for now, actually in industrial applications, you have micrometer screw gauges, digital micrometer screw gauges, right? Digital vernier calipers. If I quickly show you, so this is a image of a digital vernier caliper. Right, mostly in the industry, this is using now, because it is there. People do not have time to find the least count first and then to read. In industry, we have digital ones, so they have an accuracy of 0.01 millimeters. Right, some of them have up to 3 decimal points, 0.001 decimal millimeters, because they are electronic, no. So we can take the very high accuracy. This is a electronic vernier caliper. So there are a lot of uses of this one. You actually can push them together and you can press the 0 button. Then everything becomes 0. That means if there's any 0 error, you can remove that one. So no 0 error using this one. When we are using the analog ones, not the digital ones, then you have trouble, right? But in our A level, we have to still use the analog vernier caliper, right? That's why actually we have to learn about that. And about the digital micrometer, you see, this is a digital micrometer screw gauge. The same thing, we have the analog part also, but you can see there's a digital one. These are the things that industry actually uses, but they are a bit expensive. So in ISCO laboratories, you don't find these things because they are a bit expensive, but you find the analog one. So if you know to read the analog one, then it is more than enough. And digital one is very simple, but you must know how to read the analog one. That's the expectation, right? Okay. So these are the things about the measuring instruments. So you can read actually on them. Then we can actually go to one of the interesting parts in physics. The next week converts scalar quantities and vector quantities. This is one of the most important as well as an interesting part where you can do a lot of questions also. And for math student, this will be a help because they have to learn about vectors in maths also. So it will be a very support for you also. Without learning vectors, we cannot go to the biggest part of the physics. One of the biggest parts, biggest contents. You need to mechanics. You cannot go to mechanics without knowing vectors, right? So after this one, this basically mechanics, right? So we have discussed a lot of things on mechanics, right? Okay, so this is our plan. So we will complete the spherometer on next Tuesday, and then on the same day we will start vectors. So don't miss that one because that is one of the most important parts, like the graphs. So everywhere in physics we have to use vectors because force is everywhere. So the force is a vector quantity. So how to work with force, then we have to learn the vectors, right? So even in the advanced physics courses also we are using vectors, right? Most of the questions are basically vectors because vector is a direction and magnitude. So you will learn them in detail, right? So if you have any question, please raise now. So as I mentioned earlier, I have given you the tutorial. So you will receive the printed one later. I will send with the mechanics tutorial set, that one. Okay. So if you have any question, please raise now. Okay. So as there are no questions, so we can close for today then. Right. Okay. Thank you very much for joining, and please continue working hard, and please refer the content, and please do the questions again and again. Okay. Then have a nice day. Thank you very much for joining.